Did you know that the Great Red Spot, a colossal storm that has existed for more than 350 years, is not merely a surface cloud vortex, but actually extends more than 300 kilometers deep into Jupiter's atmosphere? In 2011, NASA's Juno mission opened the door to unprecedented insights into the giant planet Jupiter. Its magnetic field, nearly 20,000 times stronger than Earth's, revealed a strange internal structure, suggesting the possible existence of a soft core deep within the planet. At Jupiter's poles, massive polygonal superstorm structures appear, remaining unexpectedly stable over time. Most striking of all, Juno recorded a shocking discovery. Deep atmospheric jet streams, stretching thousands of kilometers, flowing like vast oceans of hydrogen and potentially serving as the source of the planet's magnetic field. Now, let us move closer to the mysteries and extreme phenomena that Juno was the first to reveal. On its outer layer, Jupiter reveals intertwining bands of bright and dark clouds. What we call clouds on Earth are merely faint shadows compared to the atmospheric layers on Jupiter. The atmosphere of this giant planet is composed of roughly 90% hydrogen and about 10% helium, a composition similar to a star that lacks the mass to ignite. But don't let that simplicity fool you. Just a few dozen kilometers down, everything changes. Jupiter's three signature cloud layers, ammonia, ammonium hydrosulfide, and water, are arranged like acts in a theatrical play, each playing its own role in the dance of storms. The bright white ammonia layer paints the soft, creamy regions. Deeper lies the yellow-brown ammonium hydrosulfide layer. On Earth, clouds hang in the troposphere, just a few kilometers high, and all weather activity is confined within that limit. Jupiter is different. There is no clear boundary between atmosphere and planetary interior. There is no cloud base, only an endless ocean of gas stretching thousands of kilometers downward. Juno arrived and revealed a secret no one expected. Storms on Jupiter can reach depths of 300 to 500 kilometers, 20 to 30 times deeper than the entire troposphere of Earth. Its vast atmosphere does not merely swirl on the surface, it dives downward, carrying not sunlight, but energy and chaos. On Jupiter, wind speeds can exceed 620 kilometers, nearly twice the strongest storms ever recorded on Earth. Thanks to Jupiter's massive size and rapid rotation, these airflows get stretched and stabilized into jet streams stretching tens of thousands of kilometers. On Earth, jet streams are narrow, unstable currents that frequently change direction. But on Jupiter, they become colossal ribbons wrapping around the planet, dividing the atmosphere into spiraling bands of contrasting colors. Jupiter hosts storms wider than Earth itself, like the Great Red Spot, with a diameter of over 16,000 kilometers. What holds them in place? What fuels such persistent atmospheric systems? Juno sent back data that forced scientists to reconsider the true depth of these storms, 300 to 500 kilometers, deep enough to tap into layers rich in heat and kinetic energy. Jupiter's energy does not come from the surface. It radiates from within. This planet emits more heat than it receives from the sun, a remnant of gravitational contraction lasting billions of years. At depths of 300 to 500 kilometers, pressure becomes unlike anything on Earth. It starts to transform hydrogen, the lightest element in the universe, into exotic states, and deeper still, into metallic hydrogen. This matters because it shows that Jupiter's atmosphere is not merely a place where weather happens. It is where extreme physical processes forge matter in states beyond human comprehension. This means every storm on Jupiter is not just wind. It is part of a massive energy engine stretching from the top cloud layers all the way down to the metallic hydrogen below. Jupiter has no such boundaries. Could its chaotic atmosphere resemble Earth's primordial past before continents formed? And could distant gas giants in other star systems host weather even more violent than this? Juno uncovered another secret, one no spacecraft had ever seen clearly before: Jupiter's two poles. If the storms near Jupiter's equator are proof of nature's raw power, then the planet's polar vortices are evidence of something even more mysterious, that chaos can organize itself into structure. When Juno first flew over the two poles, it saw something no scientist had dared to claim before: an atmospheric pattern that followed none of the rules that exist on Earth. Massive storms stood motionless in stable formations that lasted for years. At Jupiter's North Pole, Juno witnessed the appearance of an atmospheric octagonal flower, 8 gigantic storms, each ranging from 4,000 to 7,000 kilometers wide, rotating around a central cyclone. On Earth, if just 2 storms touch, they either merge or destroy one another. But on Jupiter, continent-sized storms stand side by side, edge to edge, without ever becoming one. At the South Pole, things are even stranger. Instead of 8 storms, Juno found 6 also arranged in a circular pattern around the polar center, and just as astonishingly stable. There is no symmetry between the 2 poles, but both share one defining feature: extraordinary stability. Across more than 5 years of observation, Juno saw almost no change in their positions. They did not fade away, get swallowed, or collapse. They completely defied every atmospheric model humanity has ever known. Jupiter completes a rotation in just 9 hours and 55 minutes faster than any other planet in the solar system. This force not only shapes the direction of the winds, but creates invisible barriers that prevent storms from drifting away. One might imagine each storm as a colossal pillar of gas plunging hundreds of kilometers into the atmosphere, held upright by the Coriolis force like stone columns in an ancient temple, arranged not by human hands, but by cosmic physics. But Juno discovered that the polar vortices extend far deeper than the cloud layers, and this depth is the key to their stability. Each storm is a 3-dimensional system, like a massive pillar of gas with roots buried deep in the atmosphere, where temperature and pressure continuously shift. Juno also detected significant temperature differences between the cores and edges of the polar storms. These gradients create thermodynamic boundaries that help preserve their shapes. Why, in a world full of chaos, are there places where chaos organizes itself into perfect geometry? In extreme conditions, with immense energy and enormous scale, rotational forces naturally tend to reorganize. They do not break apart, but self-arrange. They do not fragment, but become form. This is not something we are used to seeing on Earth, where storms dissipate within days, because a solid surface interferes with airflow. Earth is a planet of short cycles. Jupiter is a world of atmospheric endurance. The difference between the octagon in the north and the hexagon-like pattern in the south proves that Jupiter is not a symmetrical system. When Juno came closer, it found that the polar vortices were not just meteorological phenomena. They were windows into how Jupiter distributes energy, how its air currents interact with deeper layers, and how the planet maintains stability within chaos. But the polar vortices are only the surface of a far greater mystery, one written by invisible forces stretching through the heart of the planet and extending into space, like a reminder that Jupiter is not just gas, it is magnetism, it is force, it is a beating heart powered by immense energy. And to understand that, We must go deeper into the realm where invisible rivers of energy circulate around a core unlike any other in the solar system. When Juno approached Jupiter to measure its magnetic field using highly precise magnetometers, what it found was not a smooth, uniform force field, as scientists had believed for decades. According to Juno's data, the magnetic field of Jupiter is about 20,000 times stronger than Earth's. Yet, at the same time, it contains blotches, unusually weak zones, and streaks of magnetism misaligned with the planet's rotation axis. One of the strangest findings is the Great Blue Spot, a weak magnetic region located near the equator. Not a fixed point, but one that drifts over time. What shook the scientific community was not just its existence, but the fact that it seemed to move like a current, as if it were mirroring the flow of material deep beneath the atmosphere. As researchers dug deeper into the data, they realized that this asymmetry could not come from a traditional solid core. It had to originate from a region of constantly moving matter, like a deep, bottomless ocean of metal. The force powering Jupiter's magnetic field is metallic hydrogen, an exotic form of matter that only exists when pressure reaches millions of times greater than Earth's atmospheric pressure. At that depth, hydrogen is no longer a gas. It becomes a powerful conductor. The chaotic motion of that metallic hydrogen layer is what generates the magnetic field. But Juno showed that this metallic hydrogen layer does not behave like any model humans once believed. It coils, twists, and forms invisible vortices of force. And it is these vortices that stretch, distort, and warp the magnetic field. This led to a bold hypothesis. Jupiter's core may have been destroyed. Supercomputer simulations suggest that around 4.5 billion years ago, when the solar system was still in chaos, a protoplanet nearly the size of Earth might have crashed directly into Jupiter. That impact not only failed to destroy Jupiter, but shattered its solid core, causing the primordial core to mix into the layers above. Juno discovered that Jupiter's magnetic field is not only strong, it changes over time. It is not static, it is not fixed, it responds to the movement of material deep below. All of this forms a massive system, one that no supercomputer today can fully simulate. As Juno continued to transmit data, scientists began to realize that Jupiter's magnetic field even reveals how energy moves within the planet. Weak magnetic zones like the Great Blue Spot indicate where metallic hydrogen is swirling more intensely. Stronger magnetic zones reflect regions where matter is more densely compressed. First comes lightning on Earth. Lightning appears only in cloud layers where liquid water or ice exists, just a few kilometers above the surface. But Jupiter operates under different rules. Juno discovered that lightning on Jupiter is not only many times stronger than Earth's, but also forms at much greater depths than previous theories suggested, within water cloud layers hidden beneath ammonia. This means that liquid water exists deeper than expected, creating regions of intense electrical charge, powerful enough to unleash enormous bolts of lightning that pierce through tens of kilometers of hydrogen gas. NASA observed that some of these electrical pulses are so strong they can be seen from orbit in the darkness of the planet, like bright slashes cutting through the cosmic night. But lightning is only the beginning of the story. What is even more shocking is the appearance of mushballs, strange stones formed from a mixture of water and ammonia. When Juno observed the region near the equator, where ammonia was mysteriously depleted in the upper layers, NASA asked, "Where is the ammonia going?" The answer came from a new aerodynamic model. Inside deep storms, water and ammonia meet and crystallize into dense stones with significant mass. These mushballs fall hundreds of kilometers before melting, dragging ammonia downward. This process leaves the upper cloud layers ammonia poor, a phenomenon that puzzled scientists for decades. Mushballs have never been observed on any other planet. They represent an entirely new kind of weather, a physical process that doesn't exist on Earth, where matter becomes a bridge between atmospheric layers. These ammonia stones fall like bullets through the darkness, carrying energy, matter, and chemical traces into deeper regions where pressure rises to hundreds of times greater than Earth's surface. In the past, humans believed that convection on Jupiter occurred only in the upper cloud layers, where temperature and pressure were still bearable. But Juno, through measurements of the gravitational field and fluctuations in the magnetic field, proved that Jupiter has material flows stretching thousands of kilometers deep, transporting energy through complex spiral pathways. These convection patterns are unlike anything on Earth. They have no clear starting point, no ending point, and operate like rivers of matter swirling through darkness where light never reaches. These flows have the ability to control how energy is distributed in Jupiter, explaining why the planet emits more heat than it receives from the Sunday. This is the trace of a world that has never fully cooled, a planet still living off its primordial energy from the moment of its formation. The deep flows nearly destroy traditional atmospheric models because Jupiter's atmosphere is not a static layer. It is an open system, tightly connected to the deep material beneath. When hydrogen becomes metal, it conducts electricity and generates electric currents. These currents create magnetic fields. And those magnetic fields interact with deep convection, forming dynamic patterns so complex that even the most powerful supercomputers today cannot fully simulate them. When metallic hydrogen moves in such conditions, it becomes a self-sustaining system. These deep dynamo currents are believed to be the source of Jupiter's colossal magnetic field, a field so powerful that it drags ions and plasma and alters the surrounding space environment, forming a massive radiation belt that spacecraft dare not approach. The extreme phenomena observed by Juno show that Jupiter is not merely an active planet. It is a planet that has never stopped a world still evolving, still reshaping its atmosphere, still restructuring its inner energy. When speaking about the structure of a planet, there must exist a solid heart, deep within a stable core, unchanging, formed from the heaviest materials. That holds true for Earth, for Venus, for Saturn, and it seemed as if it must also be true for Jupiter. But then Juno arrived, and the data it sent back did more than surprise us. They shattered the entire framework of old theories, forcing scientists to reopen a question that seemed settled for decades. Does Jupiter truly have a core? If it does, what is that core made of? As Juno flew past Jupiter and used gravity to peer into the planet's interior, it found that mass was not distributed the way classical models had predicted. If Jupiter had a solid core, the gravitational field should have shown signs of a dense region strongly concentrated at the center. But instead, Juno detected a diffuse, faint, unusually widespread structure. That led to a shocking conclusion. Jupiter's core is not solid, or at least not as solid as it was when the planet first formed. Measurements of moment of inertia, gravitational anomalies, and fluctuations caused by deep convection all suggested that Jupiter possesses a diffuse core, where heavy materials like rock and metal have mixed into liquid metallic hydrogen. And what is astonishing is that this core region is not as small as a planetary nucleus. It spans 30 to 50% of Jupiter's radius, reaching 20,000 to 35,000 kilometers, wider than the diameter of two Earths combined. What could have caused a solid core to break apart and dissolve into gas? To find the answer, scientists had to look back in time to the birth of the solar system, when planets were still competing for matter, colliding, merging, and surviving in an environment far harsher than anything we see today. A physical simulation revealed the most plausible scenario. More than 4 billion years ago, a protoplanet nearly the size of Earth may have crashed directly into early Jupiter. The impact didn't destroy Jupiter. It shattered its forming solid core, breaking it into countless fragments. Those fragments didn't sink to the bottom. They were pulled upward by deep convection currents. Metallic hydrogen, capable of dissolving heavy elements under extreme pressure, began to engulf the core fragments, pulling them outward and mixing them into an enormous region. Over billions of years, the original core slowly disappeared, leaving behind a fuzzy core, a vast mixture without a fixed shape and without clear boundaries. But what surprised scientists even more is that this dissolution process is still happening. Not all the heavy material has been completely absorbed. Parts of the old core may still exist in a suspended state, stretched, fragmented, and swirling. This makes Jupiter a planet still unfinished, a world still shaping itself from within, still transforming the structure of its own heart. Perhaps Jupiter is proving that stability is only a surface, and deep inside, everything continues to move, collide, and change, like the inner life of a person who seems calm but carries a world of turmoil beneath. Jupiter is unique in one way. It not only has a shattered core, but it also possesses a physical mechanism capable of keeping that core unstable for billions of years, the immense pressure that turns hydrogen into metal. Metallic hydrogen is the key. It conducts electricity, interacts with heavy elements, and creates an environment where boundaries no longer exist. At depths of tens of thousands of kilometers, where pressure rises to tens of millions of times, Earth's everything becomes fluid. So what happens when solid matter is thrown into such an illogical environment? As Juno flew closer, it detected extreme phenomena, lightning striking from cloud layers deeper than expected. Mushballs crystallized from water and ammonia plunging through the atmosphere. Colossal convection columns, transporting energy through strange pathways never before seen in the solar system. Each of these phenomena is a trace of the ongoing battle between energy, pressure, and matter within Jupiter. NASA's Juno mission has done more than just study Jupiter. It has redefined the gas giant and, more broadly, the way we understand planetary formation. The breakthrough data showed that Jupiter is not the simple theoretical model we once imagined, but a living energy system. The storms are not merely surface cloud swirls, but deep atmospheric structures stretching hundreds of kilometers. Its poles are not calm. They are dominated by polygonal superstorms that remain unbelievably stable. Locked in place, by dynamics never seen before. Jupiter, with its deep convection flows, metallic hydrogen, and unique lightning mechanisms, is still an extreme physical machine. But thanks to Juno, the veil of mystery has been lifted, allowing us to peer beyond the clouds and witness its internal dynamics. Now, Jupiter is no longer just a planet. It is a grand cosmic laboratory, a place where the secrets of solar system formation, and perhaps countless hot Jupiters beyond, may be waiting to be decoded by future missions. The journey to understand this giant is, in truth, the journey to understand our own origins. Thank you for staying with WUFO Space until the very end of this journey through the vast universe. If you found this video interesting and insightful, don't forget to like, share, and subscribe to WUFO Space so you won't miss our next cosmic adventures. Your support means the world to us and fuels our passion to keep exploring the wonders beyond.